Well, thank you for coming back for my second lecture. What I'm going to do today is continue talking about perfect graphs for a little bit. I want to show you a polynomial time algorithm for testing if a given graph is perfect. And then we'll switch gears and talk about something called the Erdős-Hajnal conjecture, which is a problem Paul mentioned in his first lecture, and I want to do more details on that. But first, let me talk about recognizing perfect graphs. So we defined perfect graphs, and I said there are many nice things about them, and one of the nice things is that there are problems that are NP-complete in general, but you can solve it in polynomial time for perfect graphs. Well, here's something that would be nice if I didn't need to know ahead of time whether my graph is perfect, right, to use this clever algorithms. If I could, you would just give me a graph, and I would test if it's perfect, and if it is, I would go and use the polynomial time algorithms for the problems that are hard in general. And if it's not perfect, I'll just say, no, sorry, there's nothing I can do, right, to get what's called the robust algorithm. Well, so the gap in that is to check if a graph is perfect in polynomial time. And that was open for a while. In fact, that was solved after the proof of the strong perfect graph theorem. There is kind of no connection really between the proof of the strong perfect graph theorem and the proof that such an algorithm exists. But I guess, I don't know, enough people learned enough about perfect graphs that suddenly problems started getting solved. So theorem, there is an n to the 9 algorithm to test if a graph, if an n-vertex graph is perfect. And of course, when I say n to the 9, I mean right, up to constants. So, all right. So first of all, who are the authors? It's so let's see if I can remember. So it's Jacques Conjos, myself, Conjos' student Liu, Paul Seymour, and Kristina Vuskovic. And this is, so it was published probably about 2005, but it was proved after the strong perfect graph theorem. So one thing to mention, so n to the 9 sounds like a pretty rough complexity, especially if you wanted to do anything with it. But in our defense, there are two bottlenecks in this algorithm. There are two completely separate places in the algorithms that take time n to the 9. So if somebody wanted to improve it, they would have to improve it in two separate places. So now let me tell you how this algorithm works. So first of all, so idea, or I should say ideas. So the first thing to know about this algorithm is that you give it a graph, and then there are two possible outcomes. One is G is not bearish, and two is G has no induced odd. Well, I guess after all of Paul's talks, I can start using the word whole. G has no odd whole. Right, so this is not the same as testing whether the graph is perfect. If I give you a graph and I get this outcome, well, then I know it's not perfect. But if I give you a graph and I get this outcome, then I don't know. I just know it has no odd hole. So what you need to do is run this on the graph and run this on the complement. And then, so I guess let me call this algorithm 1. Right, so if I run this algorithm both on the graph and on the complement, then if I ever get that G is not bearish, then I'm done. If I get G has no odd hole and I get the same thing on in the complement, then I know that G is bearish and therefore perfect, right? So to test if G is perfect, run algorithm 1 on G and on G conjugate. All right? But from now on, I'll just focus on algorithm 1. So another thing to mention about it is that this is not an algorithm to test if there is a node hole. That problem is still open, right? And that's because one of the outcomes is G is not Beige, which means maybe what it found is an odd hole in the complement. So open the complexity, so testing if the complexity of testing if G has an odd hole. And this is a different question. This is not a question that algorithm 1 answers. And incidentally, if instead of looking for odd holes you want to look for even holes, that's known, that's polynomial. And there are actually many different algorithms, and the best one I think is something like n to the 16 or something, but at least it's polynomial. Known testing for even holes can be done in polynomial time. And I'm not sure whose algorithm is the best at the moment. I think it's probably De Silva and Vuskovic, but I'm not sure. But there are many different algorithms, but by many different people. All right. So let's go back to this. So this is a hard problem, right? We don't know how to do this. So what we're going to do is do it in stages. Just like in the proof of the strong perfect graph theorem, we assume the graph contains something that was helpful in understanding its structure. Then in the next step we could assume this something wasn't present, and then we were in an easier situation than the one we started in. It's kind of the same idea here. So what you do is you test for different things so that if you find them, you know your graph is not Beige. But if you don't find them, well, you don't know yet, whether your graph is Beige or not. But at least you're now in a simpler class of graphs. You've now proved something about your graph. And the first step in the algorithm is testing for something called a pyramid. So step 1, testing for a pyramid. Well, that's why I need to tell you what a pyramid is. And what it is a triangle, and the vertex not in this triangle. And then there are 3 induced paths from the vertex to the triangle. There are no edges between the paths, so this picture is induced. And at most one of the paths has length 1. Right? So at least 2 of the paths have an internal vertex. At least 2 paths have internal vertices. And just for terminology, I'm going to call the triangle at the bottom the base of the pyramid. And I'm going to call the vertex on top the apex. And that's just to have words. So suppose I could test for this, and suppose I found the pyramid. Then I claim I can stop and say my graph is not Beige. Why? Because so let's look at this pyramid. There are 3 paths. So 2 of them have lengths of the same parity. Let's say these 2. But now look at this induced cycle. It's some parity plus the same parity plus 1. So that's odd. So and I use here that at least two paths have interiors, because there's one situation when this is not a win, right? In this picture, it's true that I don't know what that is. It's true that these 2 guys have the same parity, but this is not an odd hole. This is a triangle. But I know that's not going to happen. I know at least at most one path has length 1. So theorem Beige, G Beige implies no pyramid. Right? So if I find a pyramid, I can stop and say the graph is not Beige. If I don't find a pyramid, I've made my life easier. So let me show you how you look for a pyramid. So this is the first step that takes time n to the 9. I'm going to show you kind of the general idea of the algorithm, and it will take longer than n to the 9. But you can then streamline it and bring it down to n to the 9. But this is not for the level of detail of this lecture. All right. So here's the idea. So I'm going to, well, okay, so what's the problem with looking for a pyramid, right? The problem is, so I can look at, let's say, these 4 vertices, and then I want to know if I choose path like this, does it make a pyramid or not? But the problem is there are many different paths I can try and choose, and some of them make pyramids and some of them don't, and it doesn't work algorithmically to just try and look at some path. But it would be nice if I could prove a theorem that says, well, actually, for all paths, or for more or less all paths, either the answer is yes or the answer is no. It doesn't matter what path I choose. And that's basically what you prove. I mean, up to some details to make it true. So what you do is you prove a theorem that says that if I select 10 important points in my pyramid, and the 10 important points is the 3 vertices of the base, the apex, the 3 neighbors of the apex, and then the 3 midpoints of paths from here to there, from here to there, and from here to there. And if I promise you that the pyramid I started with was the smallest pyramid in the graph, then it doesn't matter what path I choose from here to there, and it doesn't matter what path I choose from here to there, and in the other 4 places, as long as I choose some shortest path, I'm going to get a pyramid. Right, so once again, if I start with the shortest pyramid in the whole graph, and I look, and I fix these 10 vertices that I've made solid, and then I select any shortest path here, any shortest path here, any shortest path here, any shortest path there, and there, then what I'll get is a pyramid. Well, almost true. For example, I need to be a little bit careful. I want shortest path from here to there, but not containing neighbors of the other solid vertices. And there's some more details like that. But these are all things you can do algorithmically. There are now 10 important vertices, and you're being careful to avoid their neighborhoods and so on. But apart from that, what you do is you look for shortest path. So theorem P shortest pyramid in G, and shortest means as few vertices as possible. And then, so let's have names. This is called B1, B2, B3. This is called A. This is S1, S2, S3, M1, M2, M3. And let's say that we call those P1, and this is Q1, and so on. Let Pi be a shortest path in G, delete the neighborhoods of all the important vertices. Right, and the important are the vertices that have names. So Pi is the shortest path from Si to Mi, and then Qi is the same, except I'm going from Mi to Bi. Then the union is a pyramid. Then the union, then these paths make a pyramid. Right, so if you believe this gives you an algorithm. Just go through all 10 tuples of vertices and see if you get a pyramid in this way. If there was a pyramid in the graph, then eventually you'll find this 10 tuple. You'll find the 10 tuple of important vertices that came from the shortest pyramid, and then the theorem will tell you that tells you that what you constructed is a pyramid. And if there wasn't a pyramid in the graph, then of course you'll never find it. Right? So algorithm, look, so examine all tentuples of vertices of G, check if so this construction gives a pyramid if yes, you say G has a pyramid. If no, you say G doesn't have a pyramid. If no, I'll put no. All right, and again, so half of this is clear. Half of this is because if I can see that I found a pyramid, then the graph has a pyramid. But if I didn't find a pyramid, well, then by this theorem, I know there's no pyramid in the whole graph. All right. So now I just want to prove this theorem, or at least prove a little bit of this theorem. So proof of the theorem. Well, so here's my shortest pyramid. Here are my 10 important vertices. And it's enough to check the paths one by one. It's enough to check that if I take any, if instead of this I take any shortest path from here to there, then what I get is still a pyramid. So let's check that. So here is some shortest path, and it avoids all the important neighborhoods. And now I want to prove that I can substitute the red path instead of the white path, and I still get a pyramid. Well, so suppose not. Then there is some vertex in this red path that has chords, somewhere in the pyramid where it's not supposed to. So first of all, is it possible that all I get is chords to here? Well, no, because that means I can find a shorter pyramid in the graph, right? You kind of go like this and you shortcut, and then this is at least so this is at most as long as that, because this was the shortest path, and now I've managed, instead of going this plus that, I'm going, I managed to make it shorter. So that can't happen. So there's some vertex somewhere that has chords, that has edges into this area of the pyramid. And let's look at the lowest such vertex. So here it is. This vertex has neighbors there somehow, but this area is clean. This area doesn't have any chords anywhere. All right. So now there are three different cases. Case one, and what I'm looking at is what kind of neighbors this vertex has in this cycle. So case one, this vertex has two non-adjacent neighbors in this cycle. Then I claim I can find a shorter pyramid. I'm going to keep the same base, and I'm going to make this my new apex. And I go down here, and I go there, and I go there. And it's shorter because I saved all of this, and yet I know that this was at most as long as that. And there are some details, because how much really did I save, and then there's two extra edges here, but you can work it out. So that's the case when this vertex has two non-adjacent neighbors. Case two, this vertex has a unique neighbor. So then what you do is you build a pyramid with this base and this apex. You go this way, and down and around like that. And again, I saved all of this area. So the third case is different. In the third case, this guy has exactly two neighbors in this cycle, and they're adjacent. Right? So there are three things. Maybe there are two non-adjacent, maybe there's exactly one, maybe there's not exactly one, so there are exactly two and they're adjacent. So now I'm going to do something different. Now I'm going to build a pyramid with this base. Right? This is another triangle, so I can use it as base, and this apex. And what you do is you go down here, you go that way. So far I used precisely all of this cycle. And now the third pass is tricky. The third pass is like this. So first of all, this third pass is safe, right? Because, so maybe like there's some edges here, but then I'll shortcut that, I don't mind. But there are no edges from this white part to that cycle, and this former red path is also safe. So at least this path doesn't have any chords to where it's not supposed to. Really, I built a pyramid. Now the question is, why is it shorter? And that's where we use the fact that this was the midpoint of this path. So what did I do? I went this length plus some of the red length. But this length is more or less the same as that length. And then the part of the red length is strictly less than this white length. And so that's why it became shorter. And again, there are some details you need to do. All right, so that proved that any shortest path I take here is as good as the original path there. Now we need to do it on the bottom, but it's the same argument, and maybe I won't do it. So that's the proof of this theorem, and now we have an algorithm to test for pyramids.
So when you guess a middle vertex, do you allow to be equal to some other vertex?
Yeah, yeah. If the path is very short, then you have to. And there's a rule for how to break ties and so on. Anything else? Oh. So now I've made progress, right? If I found a pyramid, I just stop, and otherwise I can assume my graph doesn't have a pyramid. So the next step is actually easy. The next step is looking for something called easily detectable configurations. So step 2. And what that is, again, I'm looking for some things in the graph that if I find them, I know the graph is not Bayesian. If I don't find them, I've learned something about my graph. I'm now in an easier situation than where I started. So there are 3 of them. I'll show you 2, and I won't show you the third one. So the first easily detectable configuration is this, right? And so it's a 5-con. So you can go through all 5 tuples of vertices, check if they make an induced cycle of length 5. If they do, you stop. If they don't, you now know your graph doesn't have 5 cons. The second easily detectable configuration is a little bit more complicated. So what it is the following. You have a 3-edge path, and you have a 2-edge path and between some 2 vertices, and I don't care what edges I have here. And now I have another path from here to there. The reason I'm making this path red is because this so far has 5 vertices, but this is just some path. And this path has a property that he doesn't have any neighbors on it, and he doesn't have any neighbors on it, and he doesn't have any neighbors on it. So I can test, algorithmically if such a thing exists. I go through all 5 tuples of vertices, that look like this. Then I delete the neighbors of those 3, and then I check, is there still a path from here to there? So that's not hard. But now I claim if I found it, I can stop. Because why? Suppose my graph were Bayesian. Then what's the length of this path? It would have to be even, because I can complete it to a hole through this. But it also has to be odd, because I can complete it through a hole to this completion 1, 2, 3. So in a Bayesian graph, this can't happen. All right, and then the third configuration, I won't show you where it is, but it exists. All right, so now I know even more about my graph. It doesn't have any pyramids. It doesn't have any easily detectable configurations. So now the idea is, remember, I would like to look for an odd hole in my graph. And what I would like to do is kind of do the same trick as here, as I did for the pyramid. Prove that if I select some important vertices and I look at shortest path between them, that would give me an odd hole no matter what the paths are. Except that's not true, because if, say, this is my shortest odd hole, and I have some vertex, with lots of neighbors in it, well, then the shortest path from here to there is this path. It's not the path in the hole. And it doesn't look anything like the path in the hole. So what I would like to do is get rid of vertices like this. So there are two remaining steps. One is to show that really if I get rid of vertices like this, then this kind of an idea works. And then the second step is to prove that I can get rid of vertices like this. So let me say C is a hole, V not in C is major with respect to C. If its neighborhood, if it has many neighbors, so if its neighborhood is not contained in the 2H path. Maybe let me say first what the minor vertex is. It's minor if n of V intersect V of C is contained in a 2H path. Right, so a vertex is minor if it has one neighbor, or two adjacent neighbors, or three consecutive neighbors, or two neighbors at distance 2. Right? And maybe if it doesn't have any neighbors, I'll also call it minor. So this is minor, and everything else is major. It's major if it's not minor. So the first theorem is that if you don't have any major vertices, then that kind of an idea works. So theorem that C be a shortest odd hole in G. Assume G has no pyramid, no easily detectable configuration, and there are no major vertices with respect to C, and no major vertices with respect to C. Then what I do is I choose 3 equally spaced points on C, and I choose shortest path between them, and that gives me an odd hole. So this is my hole C. I'm going to choose 3 points called, I don't know, P1, P2, P3. At P1, P2, P3, be equally spaced on C, right? So this distance is about a third of the length, this distance is about a third of the length, this distance is about a third of the length. And now let's let Q1 be shortest path from P2 to P3. And again, I need to be a little careful. I need to delete neighbors of P1, say. Let's say in P of G minus N of P1, in G minus that. Right, so I choose some path here, some shortest path here called Q1, and then similarly I have Q2, which is from P1 to P3, and I have Q3, right? So Q2 is here, and then I have Q3 from P1 to P2. So Q3 is here. And then the theorem is that the union of the Q's gives me an odd hole of the same length. Let me leave this. So let me just finish writing it now. Then Q1 plus Q2 plus Q3 is an odd whole integer. Yes?
So, what was the third computation?
I'm not going to tell you, it's complicated. Anything else?
And how do you make sure that this is an odd whole?
Sorry, so you're asking why this is true?
Okay.
Anything else?
Oh, okay.
Yeah, I mean, I'm about to say it. I'm not saying it's a bad question, I'm just about to say it. Is there anything else that I'm not about to say? All right, so how you prove this theorem? You prove it basically the same way we proved the pyramid theorem. You take your shortest odd hole and you look at the three vertices, and then you look at, you try to replace this by shortest path from here to there, and you say, if I use the red path instead of the white path, it's still an odd hole. It's still, a hole of the same length. And the way you do it, you look at the first vertex with chords, and it's more complicated, but it's the same kind of idea. I mean, that's as much of the proof as I was going to do. So, anything else? All right. So what this does, this allows you to look to algorithmically find an odd hole if you're guaranteed that there's a shortest odd hole with no major vertices. So algorithm, if G has a shortest odd hole with no major vertex, can find it by examining all triples P1, P2, P3 and shortest path. Right. Q1, Q2, Q3. Right, and again, so why? So if I look at every triple in the graph and I look at three shortest paths, right? Well, if I ever see that this is an odd hole, then I stop and say I found an odd hole. But if I never found an odd hole, then I claim I know there is no odd hole. There is no shortest odd hole in the graph with no major vertex, because if there was one, then when I'm looking at this hole and at those three vertices, the theorem would tell me I would find an odd hole, right? So now there's a gap still, right? I know how to find an odd hole if this happens. But there may be a situation where I have an odd hole, but I don't have a shortest odd hole with no major vertex. And by the way, shortest here means shortest in the whole graph. It's not shortest among those with no major vertex. It's really shortest in the whole graph and subject to that with no major vertex. All right, so the last step is to go from a graph that has an odd hole to a graph that has a shortest odd hole with no major vertex. So I guess this can be described as step 4, and now we're going to do step 3. This is step 4. Step 3. Getting a graph. So let me say a hole is clean if it has no major vertices. A hole is clean if it has no major vertices. So step 3 is getting a graph with a clean shortest odd hole. Right, so I need to build an algorithm that starts with some graph that has an odd hole. Well, that starts with some graph, and then if that graph has an odd hole, it builds another graph that has a shortest odd hole which is clean. And then I would be done. So I need an algorithm with input G and output G prime, so that if G has an odd hole, then G prime has a clean shortest odd. Right, and then I can just run step 4 on G prime and I'll be done. Then can run step 4 on G prime. All right, so, well, okay, this is what I want. What I'm getting is a little bit weaker, but good enough. Instead of one graph G prime, I'm actually going to build polynomially many graphs. But one of them has this property. And that's good enough, because I can run step 3 on polynomially many graphs. And you know, if one of them has this property, then step 3 will detect an odd hole at some point. And so this is something that's called cleaning. And this is an idea due to Conforti and Rao. So construct polynomially many graphs G1 through Gk, so that one of them has a desired property. One of them has the desired property. All right, what you really do is, so really, we construct subsets x1 through xk of Vg, and k is polynomial in G, so that at least one of x1, xk contains all major vertices, all the major vertices with respect to some shortest odd hole C. Right, so let's just think about this. So I construct this polynomial many subsets, and one of them contains all the major vertices with respect to some hole, but it doesn't meet this hole. So then if I try to delete each of the subsets, you know, one at a time, so I make k graphs, G minus x1, G minus x2, and so on. Now here I'm at my good subset x10, the one that contains all the major vertices with respect to C. Well, then when I'm looking at G delete x10, I'm precisely in this situation. I still have my whole C, but I don't have any major vertices. Now I can run step 4 on that graph. Right, so x1 contains all the measures with respect to some shortest odd C and does not meet C. All right, so somehow I would like to catch all the major vertices with respect to some hole without hurting the hole. So now 1 of g minus x1 up to g minus xk works. And so I'll say this next thing very, very quickly. So what you prove is that you can find a small set of vertices in your graph so what I'm trying to say, okay, more slowly. So here's something that would work. Suppose I could prove a theorem that says if this is my shortest odd hole, then there is an edge, so that every major vertex is complete to this edge. So if I look at the set of all the major vertices, that set is complete to this edge. Well, then I would be in great shape. Because why? I'm going to go through all the edges of the graph, and I'm going to delete all their common neighbors. And then when I finally get to this edge, by deleting all its common neighbors, I'm going to get rid of all the major vertices. But I'm not going to hurt the hole, because nobody in the hole is complete to this edge. Right? So if some theorem like this were true, that's exactly what I need. So this is not exactly true, but the variant of this is true, and I think maybe I'm not going to do the details, but it's that kind of an idea. We find something small so that all the big vertices are complete to it, and then we find a way not to hurt the whole. All right, so let me maybe stop here, and now let me move to the next topic I wanted to talk about. Questions? Because I'm switching topics completely, so this is a good time to ask. Okay.
Where is the other n to the 9 part?
It's this. It's constructing those sets. Anything else? This, by the way, is also the part where you need to use where it doesn't test for odd holes, but it tests for Bereshness. Because sometimes you stop here when you find an anti-hole.
What is K? How big is the K?
I don't know. N to the 6 maybe? Do you remember, Paul? Something less than n to the 9. The reason I say n to the 6 is because I think it takes about n to the 3rd to process each graph. So it's like n to the 6th or n to the 5th or something like that. But I'm guessing. It's what's it called? An educated guess.
I think that's right. I think that's n to the 6.
That's the beauty of educated guesses. You can convince people. Anything else? Okay. So now let me switch gears. Now I'm talking about the Erdős-Hajnal conjecture. All right, so so as Paul mentioned, there doesn't seem to be a theorem that describes the structure of all graphs with a fixed induced subgraph excluded. So then the question is, what can you say in general what can you say that would be true if I exclude any induced subgraph that I want? And mostly people don't know, but there's a conjecture about that that Erdős and Hajnal made, and what they say is for every h, every n vertex h free graph has a clique or a stable set of size n to some c of h. Let me call this delta of h just because that's how I use it in my notes. So for every graph h, there is some delta that depends on this h, so that every graph that doesn't have h as an induced subgraph, right, h free means doesn't have h as an induced subgraph, has a big clique or a big stable set. And this is very different from not excluding H, again, as Paul mentioned in his talk, because you can construct a graph where the biggest clique and the biggest stable set have size log the number of vertices. In general, max clique is about log n, and max stable set is about log n. And again, a stable set is a set with no edges. A clique is a set where every two vertices are adjacent. All right, so, and I guess I want to say delta is bigger than 0. Is that what I mean? Yes. Okay. So, there are some cases that you can do right away. For example, if H is an edge, well then your graph is a stable set, so you can take delta to be 1. If H is if H is a non-edge, then your graph is a clique, right? Any H-free graph is a clique, so again delta is 1. If H is a 2H path, then as Paul mentioned in his lecture, any H-free graph has the structure of, it looks like this, has the structure of being in this joint union of cliques. So then either one of these cliques has size square root n, or there's square root n of them. So you can get delta to be half. And similarly, if H is a complement to a 2H path. As you notice, if you think about it for a minute, whatever you can prove for H, you can also prove for the complement of H. Oh, and I want another bit of terminology. So I'm going to say a graph H has the Erdős-Hajnal property if such a delta exists. So the conjecture says every graph has the Erdős-Hajnal property. So definition, H has the Erdős-Hajnal property if such delta H exists. And so then the conjecture is every graph has the Erdős-Hajnal property. All right. So what else do we know? If H is a triangle, right, it's Ramsey theory that triangle-free graphs have stable sets of size square root n. So delta is a half again. And I mean, there's some more, and I'll mention some more later, but not right now. So here's a nice theorem of Alon, Pach, and Shoy Moshe. That allows you to build new graphs. So if you have two graphs with Erdős-Hajnal property, it allows you to build more such graphs. Theorem, Alon, Pach, Shoy Moshe. If H1 and H2 have the Erdős-Hajnal property, and H0 is obtained from H1 and H2 by substitution, and I'll say in a minute what this means. Then H0 has the Erdős-Hajnal property. And what it means, substitution, so you have your graph H1, let's say, and now you choose your favorite vertex in H1 and you look at its neighbors called N and its non-neighbors called M. Right, so this is all of H1 now. I don't need this ellipsoid anymore. And then I have my graph H2. And now I'm going to replace this vertex by a copy of H2. So I'll take a copy of H2, make it complete to n, and anti-complete to m. And well, this part is what it was in H1. So notice it's really what you get from a substitution operation also depends on what vertex I chose. It doesn't just depend on H1 and H2. And the theorem is that no matter what vertex you choose. So let me maybe show you some of the proof because it's nice. So what we're going to prove is that if H1 has the so should I say again what substitution means? Is it clear what substitution is?
This is the second time we see it.
And is it clear? Okay. So what we are going to prove is that if H1 has delta 1 and H2 has delta 2, then H0 has a delta of delta 1 times delta 2 divided by delta 1 plus n1 delta 2. And n1 is the size of H1. Somehow, if you know that this is the number you're proving, then the proof is easy. If you need to guess this number, then the proof is hard. That's why I'm saying it explicitly. So let me show you some of the proof. There's a big calculation in the middle, which I'll just tell you how it comes out, but otherwise I'll do the proof. All right, so I'm trying to prove, so I have some graph G, it's H0 free, and it doesn't have a clique or a stable set of size that. Let me call this delta 0. No clique or stable set of size n to the delta 0. Right, n is the number of vertices in G. Okay, so then I can assume it contains H1, and in fact it contains many H1s. Every set of size, every U, for every U in V of G, so that U is at least n to the delta 2 divided by that thing, delta 1 plus n1 delta 2, right? G restricted to U contains H1. Because if I had a set which is this big and it doesn't contain H1, I would get a clique or a stable set which is this to the power delta 1, which is what I wanted. And similarly, for every U, so that U is bigger than delta 1 divided by this, G restricted to U contains H2. Right? So there are lots of H1 and there are lots of H2s. And now what we're going to show is that, right, and so let's say to get H0, I take this vertex V in H1, and I substitute and I substitute H2 for V. And what I'm going to show is that because I have lots of H1s, I also have, because I have lots of H1s and not very many H1 minus V, there is one copy of H1 minus V that extends to H1 in many ways. Right? There are many different choices for V. These are all possible choices for V. And then this is so big that it's at least this big and it has to contain H2. right? So now I'll do the calculation and you'll understand what I mean. So how many copies of H1 are there in G? Well, every set of size of this size contains a copy of H1. So let me call this number M. So every set of size M contains a copy of H1, but some copies of H1 are counted, for many different sets. So for how many sets of size M can one copy count? Well, so I fix this copy, and now I need to select the rest of the set M, so of the set of size M. So I need to select another M minus the size of H1 vertices here. Right, so the number of copies is n choose M, right, because every set of M vertices contains a copy, except there's some double counting, and the double counting is n minus n1 choose m minus n1, right? That's for how many sets one copy can count. Now, so I have this many copies, at least this many copies of H1. Now, how many copies of H2 do I have? Well, I'm just going to use a very crude bound. It's just make sure I'm using the right crude bound. Yeah, so it's just there's at least, so there's at most n choose n1 minus 1 copies of H1 minus V, right? How many copies of H1 minus V are there? Well, it's at most all possible choices of n minus 1 vertices. And that means that, right, so that some copy of H1 extends to, some copy of this extends to a copy of H1 in many different ways. So some copy of H1 minus V can be extended to H1 in at least this divided by that number of ways. Right? So some copy of H1 extends in this many ways. And now the thing is, when you do the calculation, this is big. This is at least this big. So dot, dot, dot. This is at least n to the delta 1 plus n1 delta 2. All right, and that means what? That means right, so if H1 looks like this, V and N and M, I have some fixed occurrence of N and M, and then a huge set here, all complete to N and anti-complete to N, right? A huge set of people that could possibly be V's. And it's so big that it contains a copy of H2. But that means I got my H0. All right, so that's a proof. All right, so now let's move on. And this is nice because, right, this allows you to build infinitely many graphs with the Erdős-Hajnal property. You start with one, and now you can make many. So asking, what's the biggest graph with the Erdős-Hajnal property doesn't make sense anymore because of this theorem. But what does make sense is to ask, what's the biggest graph with the Erdős-Hajnal property which is prime, which is not obtained from smaller graphs by substitution. And that's pretty small. So the by the alone path to Emotion theorem enough to prove that prime graphs, prime means not obtained by some substitution, have the Erdős-Hajnal property. So, all right, so what prime graphs are there? Well, on 3 vertices, I guess there aren't any. On 4 vertices, you only have this guy. And then you can prove that it has the Erdős-Hajnal property. In fact, the way you would prove it, graphs with no 3H paths are in particular perfect, because the node hole and the node antihole both contain 3H paths. Now let's prove that perfect graphs have the Erdős-Hajnal property. Sorry, that's not what I mean. Let's prove that perfect graphs have big cliques or big stable sets. So G is perfect. So theorem, G is perfect. Perfect implies omega of G is at least square root n, or alpha of G, alpha is the size of the biggest stable set, is at least square root n. And that's just because, well, what does it mean to be perfect? In particular, it means you can color the graph with omega stable sets, so you can cover the vertices with omega sets of size alpha. Right, so proof can cover V of G with omega of G sets of size at least alpha of G. But that means alpha times omega is at least 10, which means exactly what we wanted. Alpha is at least square root n, or omega is at least square root. So if I don't contain a 3H path, then my graph is perfect, and so it has a clique or a stable set of size square root n. So delta of the 3H path.
The size and most alpha.
What did I do? Size. Yes, thank you.
Yes.
Yes, but it still comes out. Anything else? All right, so that's graphs, and this is the only prime graph on 4 vertices. Now, what about graphs on 5 vertices? Prime graphs on 5 vertices. Well, you don't have very many, but you can check. You have C5, you have the 4H path, you have the complement of the 4H path, and you have the bool. And so this is known. This has delta, which is a quarter. But all the others are open. Now, doing this and doing that is the same, right? We said doing a graph and doing its complement is the same. So, what do you want to say next?
This delta, you know precisely, or this is...
So yes, that's the right answer. I'm going to show a construction in a minute. Anything else? All right, so it's not clear at all why the bool works so much better than anything else. One might think it's because it's its own complement, and there's some evidence to suggest that if you exclude a graph and its complement, then somehow things get better. For example, you can prove that if you exclude this and that, you get graphs with a big clique or a big stable set. I forget how big, but big. But that that theory has a flaw because this is its own complement. So it's not true that this is the winning property. One thing I should mention, so all of these are open, but there's a theorem of Stéphane Thomas or Lila Gut and somebody else, Pierre Charby, I think, that says that if you exclude any path and its complement, then you get a big clique or a big stable set. So theorem, and this is recent, this is from last year. Charby, Gut, Thomas. I think I'm listing the right authors. I'm not entirely sure. I'm sure it's these two, and I'm almost sure the third one is Shabby. So if G, so for every K, there exists delta, so that if G has no PK and no PK complement, then alpha of G is at least n to the delta, or omega of G is at least n to the delta. And the proof is, so how can I say it? The proof is not very long, but it uses some very strong tools. It uses a regularity lemma. And so, I mean, I don't know if a proof that uses a regularity lemma and then it's relatively simple. I don't know if it counts as a hard proof or an easy proof. But it's definitely a clever proof. So let me go back to the bool. So theorem. This is a theorem of Molly Safra and myself. So we proved that delta of the bool is at least a quarter. And now let me show you why it's at most a quarter. So I need to construct a bool-free graph with no clique and no stable set of size bigger than n to the quarter. Well, there are triangle-free graphs with no clique or with no stable set of size bigger than square root the number of vertices. And again, I'm shamelessly ignoring constants, so everything is up to constants. So that's I don't know, G, B, or G1, B, and N vertex triangle-free graph with no clique, with no stable set. So with alpha G about square root n. And now what I do is I take G1 and I substitute a copy of its complement for each of its vertices. So build G from G1 by substituting a copy of G1 complement for each vertex of G1. And now I claim this is the graph. This is bool-free and doesn't have big cliques or big stable sets. So claim G is bool-free. Alpha of G is about V of G to the 1/4, and omega of G is about V of G to the 1/4. All right, so why is it bool-free? Well, the bool is not obtained from anything by substitution. So that means if this is my graph G, right, which is G1 with vertices blown up, the bool, if it had a bool, it would be either contained in one of the blobs or contain at most one vertex from each blob, right? If it had a couple of vertices here and then some other vertices somewhere else, then this would be a homogeneous set in the bool. So now, all right, but now can it contain one vertex from each blob? Well, no, because G1 is triangle-free and the bool has a triangle. Can it be completely contained in a blob? No, because the blobs have no stable sets of size 3, and the bool has a stable set of size 3. So it's definitely bool-free. So now let's think about cliques and stable sets. Well, where can a clique in this graph be? Remember, G1 was triangle-free. So the best I can do for a clique is, either it would be contained in one blob, or, well, okay, I mean, the best I can do for a clique is to take two vertices of G1 that were adjacent, and then take a max clique in the blob that corresponds to one and a max clique in the blob that corresponds to the other one. But this is about square root n, and G has n squared vertices, right? So every clique of G is contained in two copies of G1, and so has size about square root n, and yet G V of G is n squared. So what about stable sets? Well, where can a stable set in G be? Well, each blob has stability number 2. So the best I can do is take some stable set in G1 and then maybe double it. But what's the biggest stable set in G1? Well, it's again about square root n, and I'm about doubling it. So every stable set in G contains at most two vertices from each copy of G1, and so size about square root. All right, so that's perfect. Okay, so the next thing I want to do is talk a little bit about the proof of the upper bound. Proving delta of the ball is at most n to the force. Is at most sorry, at least a quarter. What did I do? Did I write at most a quarter? No, I didn't. Good. So what I want to do is introduce another concept that turns out to be equivalent to having the Erdős-Hajnal property, or equivalent to something to do with the Erdős-Hajnal conjecture. And this is called alpha narrowness. Alpha narrowness. So I'm going to say G. So, okay, back up. So the Erdős-Hajnal conjecture says there's a big clique or a big stable set. I don't want to work with two outcomes, I want to work with one outcome. Now, it's enough to prove that there's a big perfect induced subgraph in my graph, right? If here's my big graph G and I'd like to find either a big clique or a big stable set, it's enough to prove there's a big perfect graph. Because then by this theorem, I get a clique or a stable set which is, square root of that. So the idea is, just a minute. The idea, look for a large perfect induced subgraph, right? And that's enough. Now, so what alpha narrowness tells you is that somehow the whole graph is not much bigger than the biggest perfect induced subgraph in it. So now with this intuition in mind, I can define what it means. So I'm going to think about functions from v of g to the 0, 1 interval. And I'm going to say f is good if f sums up to at most 1 on every perfect induced subgraph. For every perfect induced subgraph P of g, the sum v and v of p of g of v is at most 1. So this is somehow a function that's not too big on perfect induced subgraphs. And now to be alpha narrow means that every good function is not too big on the whole graph. Right? If you're not too big on perfectly induced subgraphs, then you're not too big on the whole graph. And that somehow means that your perfectly induced subgraphs are relatively big. So G is alpha narrow if for every good G, the sum of the alpha powers of G now on the whole graph is at most 1.
You want to have a function G or F?
G. For good. Right, so a function is good if it's not too big on perfectly induced subgraphs. Now, a graph is alpha narrow if I can make this function a little bit smaller by raising it to some power alpha, and then require that that sum is at most 1 on the whole graph. So alpha here is an integer. Right. So, for example, perfect graphs are 1 narrow, right? So let's prove that if you're alpha narrow, then you have a big clique or a big stable set. Here. If G is alpha narrow, then alpha of G is at least n to the 1 over 2 alpha, or omega of G is at least n to the power 1 over 2 alpha. And this used to have a complicated proof involving LP duality, but
So you use 2 alphas at this thing, right? So
say it again.
you have alpha G.
You think it's a bad idea to use alpha of G and alpha in the same place? Okay, let's see if I can do this. Let's call this beta narrow. See if this is going to confuse me completely. All right. So, like I said, this used to have a very hard proof, but now it has a very easy proof. So let K be the size of the biggest perfect induced subgraph in G. The maximum for all P perfect induced subgraph of G of the size of P. And now let's look at the function which is 1 over K everywhere. For every vertex, it's 1 over K. Well, this is a good function because every perfect graph has at most K vertices. Now, my graph G is beta narrow, so that means that the sum of the beta power of these on the whole graph is at most 1. So that means n divided by K to the beta is at most 1. But that means K is big. That means K is at least n to the 1 over beta. And now I'm going to use this theorem that's still conveniently here, that in a perfect graph I have a clique or a stable set of size square root of the size of the graph. So clique or stable set size n to the 1 over 2 beta. All right, so it's enough. If I'm trying to find a big clique or a big stable set, it's enough to prove that the graph is beta narrow for some beta. And in fact, it's a theorem of Jacob-Fox that it's equivalent. if I have a hereditary class of graphs, all of which have big cliques, polynomial size cliques and stable sets, then every graph in that class is beta narrow for some beta. But I'm not, so the other half is more difficult. I'm not going to prove that. So now let me quickly show you how you prove that bool-free graphs are, that the bool has the Erdős-Hajnal property. So first you prove a structure theorem. You prove that every bool-free graph is either basic or admits a useful decomposition. So theorem. So let's say a graph is basic if so what do I want to say? Again, let me not mess this up because this is not a good time for that. Yeah, if no hole of length at least 5 has both a center and an anti-center, both a vertex complete to it and a vertex anti-complete to it. Actually, sorry. I want to change this. G is basic. If I define it this way, there is another step which I want to skip. So I'm going to define basic to be the outcome of the next theorem. So G is basic if no vertex is both a center and an anti-center for an odd hole or an odd antihole. So what this means, if I look at a vertex, right, center means complete to, anti-center means anti-complete to. So if I look at a vertex, either there is no odd hole and no odd antihole here, or there is no odd hole and no odd antihole here. So this means for every v, either n of v is perfect, or the complement, or g restricted to that, or g delete n of v union v is perfect. Right, so that's what basic means. I guess I should have just given this definition. So for every vertex, either its neighborhood is perfect or its not neighborhood is perfect. And now we prove a theorem that says that every bool-free graph is either basic or has what's called a homogeneous set. And that just means it's not prime. It's obtained by substitution from some other graphs. So theorem G bool-free implies G is basic or G is obtained by substitution from smaller graphs. Now, so Paul mentions that there is a structure theorem for bool-free graphs. This is not it. This is an easy theorem. This is, the proof of this is maybe 5 pages. The real structure theorem is much harder. So now, we are ready to prove that every bool-free graph is too narrow. So theorem, every bool-free graph is too narrow. And the way you prove it is, right, and that would tell you that in every bool-free graph there's a clique or stable set of size n to the power 1/4. And the way you prove it is by, let's say by induction of the number of vertices. So case 1, G is basic. So here's So then what you do, so what do I need to prove? I have a good function g, and I need to show that the sum of the squares is at most 1. So there are two cases. Case 1, g is basic. So then what you do is you choose a vertex v0 with maximum value of g. And then I'm going to look at the neighbors of v0 and the non-neighbors of v0. And because g is basic, I can assume that either this graph is perfect or that graph is perfect. And by going to the complement, I can assume that this graph is perfect. Now, all right. So now I'm going to adjust my function g. I'm going to define a new function just on m. So I'm going to define g, let's say g prime of v to be g of v divided by 1 minus g of v0. And this is going to be a function just on m. Now I claim this is a good function on this graph because if I have a perfect graph here, I can add v0 to it. That would still be perfect. So that means the sum of my original g on this was at most this big. So I can normalize and still get a good function. All right. So now I'm going to inductively use the fact that this graph is too narrow. So inductively, g restricted to m is too narrow. So the sum of the squares of these is at most 1. So that means the sum of the squares of g just on m is at most 1 minus g of v0 squared. All right. And now I'll try and calculate the sum of the squares of g on the whole graph. So the sum v and v of g squared of v, it's a sum, so I'm going to break it into two. One case is when v is in n, one sum is when v is in this set or v is that vertex. And then the other sum is when v is in this set. Now for this I already have a bond, right? For this I have this upper bond. For this, I remember that v0 is the vertex with the highest value of v, or with the highest value of g. So I can replace this by g of v0 times this. Well, I'll write it down. So I can replace this by g of v0 times this. And then plus that sum, which I know is this. All right, so now remember, n was perfect. If I add a vertex complete to it, it's still perfect. So that means this sum is just 1, right? Remember, because g is a good function. So this is at most 1. So now what I get is g of v0 plus 1 minus g of v0 squared, and if you think about it for a second, is at most 1. All right? So that's the basic case. Now I'm just going to say 2 words about the other case, the case when G has a homogeneous set, which is there, when G is obtained by substitution, and then I'll stop. case 2. In case 2, G is obtained by substitution. So that means G looks like this. There's some homogeneous set, some set H, and then there are people complete to it and people anti-complete to it. So now I'm going to break this graph into 2, or I should say, actually, wrong. I'm going to squash H to a vertex. I'm going to look at this graph. And now, so I have my function G. Now I need to define a new function on this graph. Well, so here I'll just inherit it, but here I'm going to put the weight, the biggest weight of a perfect graph in H. The maximum of the sum, the maximum of P perfect induced subgraph of H. And then the sum of GV, V, and V of P. Right? So what I'm going to put here is the biggest contribution H can have to the function G. And then I'm also going to use the fact that on H I can normalize. So this is going to be one graph with one function. Now I'm going to, just on H, I'm going to define another function called G prime. And what I can do there is just normalize, right? So let me call this number K. Now I can look at this function. And this is a good function on H. And now you use the fact that H is too narrow, so this sum is the sum of those squares is at most 1, and this graph is too narrow, so the sum of K squared plus all the squares here is at most 1, and it comes out exactly. Yeah. This and that are both too narrow. Combine, get the G is too narrow. All right, then let me stop here. Thank you.